We know that a charge experiences a force when it's near another charge. Therefore, we can say that around every charge, there exists a region of space, a region of influence, where other charges will experience a force. This region is called an electric field. Let's understand this better with a simple analogy. Imagine a classroom full of noisy students. Suddenly, the teacher walks in, and the class goes silent. The teacher has an invisible region of influence around them. It's not visible, but it can definitely be felt by the students. It's just like an electric field. Charges are like students that respond to the invisible field. Now imagine all the students leave the classroom, but the teacher is still there. Does the region of influence disappear? Of course not. The teacher's ability to influence is still there. It's just that there's no one around to feel it. The same goes for electric fields. They exist around charges whether or not other charges are present to experience them. The term field in physics refers to something that is spread out in space, a region where the physical quantity is defined at every point. For example, take a temperature field. It shows how temperature is distributed across a region at a given time. Each point has a temperature value, showing how hot or cold different parts are. Similarly, an electric field shows how the electric force, experienced by a charge, varies across space. A temperature field is a scalar field, only magnitude, no direction. But an electric field is a vector field. It has both magnitude and direction at every point. The strength of the electric field at a point is called the electric field intensity. It varies from point to point, as indicated by arrows of different lengths. Let's try to find electric field intensity near a charge. Consider a positive charge. Let's call it Qs, since it is the source of the electric field whose strength we want to examine. Qs creates an electric field around it. Now, pick any point near this charge. We'll call this point P. Let r be the distance between the charge Qs and point P. To determine the strength of the electric field, a test charge, Qt, is introduced at point P. Qt experiences a force due to Qs. A test charge is necessary because an electric field cannot be observed directly. It can only be detected through its effect on other charges. To better understand this, let's go back to our teacher-student analogy. Suppose we wish to evaluate the influence or effectiveness of a teacher. Let's call it teaching field intensity. One way to estimate this is by examining student performance. Assume student A scores 5 out of 100, while student B scores 90 out of 100. Can we conclude that the teacher is effective or ineffective based on these marks? The answer is no, because a student's performance depends on both the teacher's influence and the student's own ability. In a similar manner, the force experienced by a test charge depends on both the source charge Qs and the test charge Qt. However, we know that electric fields exist around charges whether or not other charges are present to experience them. This implies that electric field intensity must not depend on the test charge, even though a test charge is used to measure it. This is like the teacher's influencing field existing without students, hence being not dependent on students' ability. To eliminate the influence of the test charge, we divide equation 1 by Qt. After cancelling Qt, we can see that the right-hand side only depends on the source charge Qs and the distance r. Hence, the ratio of force F to the test charge Qt is the electric field intensity. Suppose we place a unit positive test charge at point P. Then the force on the unit positive charge is obtained by substituting Qt equals 1 in the equation 1. By comparing equation 2 and 3, we can observe the similarity. Therefore, we can say that the electric field intensity at a point is numerically equal to the force experienced by a unit positive charge placed at that point. Do note, it's only numerically equal, not exactly equal, because the units are different. Electric field intensity is in newtons per coulomb, while force is in newtons. It's like comparing 10 apples with 10 oranges. Sure, the numbers match, but apples and oranges are not the same.